Before we begin, we wanted to cover a few housekeeping items. At the bottom of your screen are multiple application widgets you can use. All the widgets are resizable and movable. If you have any questions during the webcast, you can submit them through the Q&A widget. We will try to answer these at the end of the event. A copy of today's slide deck and additional help materials are available in the resource list. We encourage you to download any resources or bookmark any links that you may find useful. You can also find additional answers to some common technical issues located in the help widget at the bottom of your screen. An on-demand version of the webcast will be available approximately 1 hour after the webcast and can be accessed using the same audience link that was sent to you earlier.
Good morning, everyone. My name is Chintan Shah. I'm the product manager at NVIDIA managing DeepStream SDK. Recently, we announced DeepStream 4.0, and today in this webinar, I'll go over accelerating real-time AI-based video and image analytics using DeepStream SDK. Here's the agenda for today's webinar. I'll start with introduction of what is IVA, or Intelligent Video Analytics, and how it can provide efficiency and safety. Then I'll dive into how we can use DeepStream to solve the challenges in computer vision and IVA. I'll go over major features in DeepStream 4.0, including high performance that you can achieve. Then I'll go over several industry use cases that can be solved using DeepStream. For several of these use cases, we have built a full end-to-end proof of concept application. DeepStream can help developers extract business insights for retail, understand citywide traffic patterns, automate industrial inspection, and can optimize warehouse logistics. All these systems share commonality with using cameras to generate analytics. After that, I'll jump into how a developer can get started with DeepStream. I'll go over several examples packaged in the SDK that developers can start with. Then finally, we'll show how to deploy your applications using Docker containers available on NVIDIA NGC. Then we'll conclude with the Q&A. Cameras are everywhere. In fact, it is estimated there will be about 1 billion cameras by 2020, and they are found in parking lots to shopping malls to warehouses. They represent perhaps the most deployed IoT sensors out there, and it's super rich with data. Extracting meaningful insights from these cameras can help bring operational efficiency and safety. Few of the examples highlighted here are access control in a building. This can permit an individual to enter a premise. Public transit. Cameras in public transit can make our surroundings safer. In an industrial setting, using cameras, you can automate inspection that is tedious and time-consuming for humans. Other applications include smart logistics, for example, automated way of detecting and flagging packages on a conveyor belt. Traffic engineering is another area that can benefit from intelligent analytics. It can help city planners understand the traffic patterns, which can help reduce traffic congestion. In a retail setting, IVA can be used to generate rich business insights. It can also be used in loss prevention and automated checkout. Think of the Amazon Go store and how many cameras it has. The potential of using video analytics are enormous and can truly make our cities and businesses intelligent. The thing that is common across all these industries is you need to process pixels from camera to collect insights. The type of application might differ, but the flow from pixels to insights remain common across all the use cases. Some application might require processing on the edge, either on the edge device such as NVIDIA JETSON or on-prem servers. The use case for edge range from security to monitoring the construction sites to manufacturing. The on-prem server could be as simple as an AI-based NVR, a network video recorder for small business. For applications requiring large numbers of camera, you can deploy a server using NVIDIA T4 GPUs. For other applications, all the processing might happen on the cloud. DeepStream offers the flexibility to deploy on the edge or on the cloud. DeepStream also integrates with NVIDIA's Transfer Learning Toolkit, or TLT. You can use TLT to train a pre-trained model for your application. The pre-trained models are available on NGC, NVIDIA Cloud Registry. You can pull the models from NGC, retrain it with TLT, and deploy on DeepStream. Today, in this webinar, I'll go over several use cases from industries that can be solved using DeepStream.
This is the entire DeepStream software stack, from application level all the way down to the hardware. At the very top is the application. Under the application layer is the SDK. DeepStream SDK is a streaming analytic toolkit which consists of various hardware-accelerated plugins that provides the highest throughput for any computer vision and IVA applications. For example, for decode, we use the NVIDIA's NVDEC, hardware-accelerated decode. For AI inference, we use the CUDA cores in the GPU or the DLA core in the JETSON AGX Xavier. For deployment, developers can deploy their DeepStream application using bare metal system running Ubuntu Linux, or they can deploy it in container using NVIDIA Docker Runtime. NVIDIA Docker Runtime enables the use of GPU and other acceleration from within the container. The entire DeepStream application can be packaged in a Docker container. In addition, we provide several reference application and orchestration recipes to kickstart any IVA projects. Finally, to connect to the cloud, DeepStream supports communication to the Microsoft Azure IoT Cloud using the Azure IoT Runtime. This allows seamless connection to the cloud to run analytics and manage devices. The next level of the stack is the CUDA-X stack, which lists various NVIDIA software technologies that are used by DeepStream plugins. At the very bottom is the full hardware stack that can be used to deploy DeepStream application. DeepStream application can be run on NVIDIA JETSON platforms or the data center GPUs such as T4s or V100. In our DeepStream journey, 4.0 represents a major step change in capability, scalability, and portability. The soul of DeepStream 4.0 is to support all the platforms at NVIDIA with a unified SDK. This goes from newly introduced JETSON Nano to all the way up to data center GPUs. Developers can start development on one platform and then port it to other platforms. Same code base, different platforms. With DeepStream 4.0, we are offering turnkey integration to connect to Microsoft Azure IoT Hub via the Message Broker plugin. Microsoft Azure IoT Hub can be used to connect, manage, and monitor IoT edge device. We released deployment containers for GPU products for DeepStream 3.0, but for 4.0, we're bringing the Docker capability for JETSON platform. You'll be able to deploy and manage DeepStream application using containers. Images can be pulled off from NGC, the NVIDIA's Cloud Registry. For 4.0, we're also releasing new models and capability for industrial and retail use cases. There are new models to support monochrome or grayscale images and image segmentation. In addition, we're adding hardware-accelerated JPEG decode and encode. And finally, for the first time, we're opening up source code for 3 of our main plugins. This gives greater flexibility and control to our developers. The 3 that we're opening up are Decode, Inference, and the Message Broker plugin. This is a very high-level view of what a typical IVA graph looks like, from pixels to insights. Pixels from the camera are captured, decoded, and pre-processed. Once it's pre-processed, we apply deep learning or AI to get some insights from the video. This insights can be viewed on a screen or can be sent to a data center or cloud for further analytics. Today in this webinar, I'll walk you through all the different aspects of building an IVA pipeline. This pipeline for processing and understanding video or image is industry agnostic. There might be some nuances that are different between industry, but overall the workflow remains very similar. Now let's see how we can create this workflow using DeepStream SDK. DeepStream SDK is a streaming analytic toolkit. Plug-and-play architecture built on open source GStreamer platform. This allows developers the flexibility to not only use our plugins, but they can use other open source plugins or create their own plugin and use it in the pipeline. This is a typical IVA pipeline constructed with DeepStream plugins. And at the bottom, it shows the underlying hardware that is used by the plugin. The first step is capturing the streaming data. This could be coming from RTSP stream, from a file, or from a USB or a CSI camera. After capturing, the next step is decoding the stream. Decoder plugin uses the NVDEC, the hardware accelerated decode engine on NVIDIA hardware. This is different than the CUDA cores on the GPU. After decoding the frame, there might be some pre-processing that needs to happen. This could be image conversion, image scaling, cropping, or if the stream is from a 360-degree camera, then you need to dewarp the image. There are various accelerators for this operation. The next operation is the inference, which performs object detection, classification, and segmentation. This is run on the GPU or on DLA, the deep learning accelerator available on JETSON AGX Xavier. After inference, you might need to track the object for insights. And finally, the last step is to view the video on the screen with the attached metadata or send just the metadata to the cloud for further analytics.
This is the list of the plugins that are included in DeepStream SDK. These plugins are accelerated for NVIDIA hardware. I'll talk about a few of these in greater detail in the later part of the webinar. The first one is NVIDIA for Linux, plugin for video and image decode and encode. This uses NVDEC and NVEnc accelerators. The second one is NVInfer. This is an inference plugin which uses TensorRT, NVIDIA's inference accelerator. This can do object detection, image classification, and segmentation. Third is NVTRACKER. We provide several reference trackers such as KLT, IOU, and NVDCF. Fourth is Message Broker. This allows the capability to send messages to the cloud using various protocols. For more information about how to use this plugin, refer to the plugins manual in the documentation. Here are the real-time performance that you can achieve with DeepStream on various NVIDIA platforms. The end-to-end app used to generate this performance number is packaged in DeepStream SDK. The SDK also comes pre-packaged with all the detection and classification models. We can run as many as 8 streams in a tiny JETSON Nano to all the way up to 68 streams in an NVIDIA T4. For object detection, we use a 4-class ResNet 10 network which can classify person, car, two-wheelers, and road signs. For JETSON AGX Xavier and T4, we're also adding 3 secondary networks to do classifiers on the detected objects. If you want to duplicate this performance on your system, please see the DeepStream development guide.
In the next part of the webinar, I'll walk you through several industry use cases that we build with DeepStream SDK. Extracting business intelligence is vital for today's retail industry. It can help retailers manage inventory better, improve customer experience, and reduce loss. Cameras provide a rich source of intelligence. One of the use cases in retail is tracking. To get accurate insights on customers, it needs to accurately track people as they move around in the store. On the right is the solution that is constructed with DeepStream SDK. The plugins listed in the pipeline are all provided in the SDK. DeepStream can help retailers understand video using deep learning and AI. One of the plugins in the SDK is a Tracker plugin. Tracker will assign ID for each detected objects. This unique ID will be kept on the person of interest until the person leaves the field of view. With the tracker, you can accurately count the number of people in the store at any given point and how long they spend across each aisle. DeepStream ships with several reference trackers ranging from high performance to high accuracy. This is a high-level view of the NVTRACKER plugin. The input to the plugin is the video buffers plus some metadata about the object. This would be the bounding box location of the detected objects. What comes out of this plugin is a buffer plus some modified metadata for the object ID. The way a tracker tracks an object is by assigning each object a unique object ID. This is added to the metadata field to distinguish one object from another. The various trackers available are NVDCF, KLT, and IOU. Developers also have an option to add the custom tracker in the tracker plugin. We'll have a tutorial in the future on adding a custom tracker in the DeepStream pipeline. Developers can configure various parameters such as tracker width and height, tracker type, and GPU ID for GPU-based trackers. Now let's compare the three trackers that are provided. The IOU tracker is a very lightweight CPU-based tracker which provides the highest performance. The downside is it's very prone to frequent ID switches and thus it's not suitable for fast-moving scenes. The use case of IOU tracker is to track objects that are sparsely located within distinct sizes. The next is the CPU-based KLT tracker. This works reasonably well for simple scenes but comes at a high cost of CPU utilization. It is also extremely susceptible to changes in the visual appearance due to noise or perturbation, such as shadows, non-rigid deformation, autoplane rotation, and partial occlusions. The third and the final tracker is the GPU-based NVDCF tracker. This is highly robust tracker and works reasonably well against partial occlusions. This is less prone to ID switches. The downside of the NVDCF tracker is it's slower than KLT and IOU due to increased computational complexity. Since it's a GPU-based tracker, it will reduce the total number of streams processed. So overall, with three trackers, developers can choose between a tracker that offers the highest performance or a tracker that offers the high accuracy and robustness when making their choice. Another place that employs lots of camera is a city. If you look at any traffic light, you'll see several cameras at an intersection. Compound that over an entire city, now you have thousands of cameras that you need to analyze. Drawing insights from the swaths of camera can help reduce traffic congestions in our cities and makes our road safer. Anomalies on the roads can be detected immediately and alert authority. In addition, transferring terabytes of video data to the cloud might not be feasible due to bandwidth limitation. So, you want a solution that analyzes the pixels on the edge and transfers only the vital metadata to the cloud or analytics server for further insights. On the right is the solution for a smart city, which does the perception on the edge and sends just the metadata to the cloud. DeepStream, with its message broker plugin, offers the ability to seamlessly connect from the edge device to the cloud. In the next few slides, I'll go over the message broker plugin in more details. The NV Message Converter and NV Message Broker plugin allows a perception graph to connect to an analytics server or cloud through the message bus. It takes the input metadata and creates messages that are sent over the supported protocol. The Message Converter plugin will parse the base metadata format and generate the schema. The schema can be one of the predefined schema in DeepStream or can be fully customized. The payload data is in JSON format. The Message Broker plugin sends this payload from the message converter to the server using one of the defined protocols. There are a few reference applications to help you get started with using the Message Broker to communicate externally to the cloud or a server. Let's dive into different protocols that are available in DeepStream 4.0. We realize that connecting to a cloud service is extremely important for an IoT application. As a result, in addition to the Kafka protocol adapter, which was supported in DeepStream 3.0, For 4.0, we're adding support for framework-specific client, such as Microsoft Azure IoT. This uses the MQTT protocol. The adapters provide out-of-box capability for DeepStream application to publish messages to Azure IoT Central. The third protocol we support is AMQP using the RabbitMQ library. Please refer to the full chapter on Message Broker in the plugins manual. This shows all the different knobs that you can play with in this plugin. This is an end-to-end application for intelligent traffic system. You have the perception pipeline where pixels are converted to insight on the edge. Then an analytic workflow will take this metadata and create searchable analytics and display it on a web browser for visualization. In the trajectory processing part of the analytic, the image coordinates are mapped to the geo coordinates using the road network and the camera calibration. The camera calibration is provided externally to the analytic engine. The ROI or region of interest will focus the analytics only on the car on the road and not on the cars that are parked. The road network can also help calculate speed on the road segment. There are several anomaly detection implemented. Some are rule-based and some are from LSTM model. The rule-based could be speeding violation or unexpected stop. The LSTM-based could be car driving in the wrong direction. It looks at sequence to sequence, and anything that deviates from the norm will be classified as an anomaly. With the search indexer, you can search for any events or anomalies. You will see the entire pipeline in a demo. In addition to the metadata, the streams from the camera are sent to the VMS. This is used to record, view, or search any streams. And finally, all the information can be accessed with the web browser. Let's explore the architecture of the analytic application. The deployment of the analytics can be in a cloud or a Kubernetes cluster. Kafka Message Broker reads the message from the edge device and sends it to Apache Spark Engine and Logstash. Apache Spark will analyze the streaming data and build trajectory maps of the car and detect anomalies. Logstash for ETL will process the raw data and send it to the search indexer. The search indexer is implemented using Elasticsearch. VMS will record the live streams coming from the camera for playback of anomaly and display it on screen. This API will show speed, number of cars, time traveled between a given corridor. Kibana is used for creating this analytic dashboard, which provides easy-to-use interface from the browser. Now let's see all in action. Over the next few videos, you'll see a demo of the entire application at work: perception, analytic, and visualization. Let's jump into the perception demo. On the next clip, you'll see a perception demo from our ITS project.
What you see in this video is pixels to perception. The perception is performed using DeepStream on the edge. The AI engine detects and tracks the car in the frame. This metadata is extracted and is sent to the server using the Kafka Message Broker. Now you see a car going in the wrong direction. The analytics server records this as an LSTM-based anomaly and will inform the control center.
In the following clip, you'll see a short demo of our analytic dashboard.
In the analytic dashboard, the y-axis shows the names of the intersection and the x-axis shows the number of unique objects or cars that pass through the intersection in the last 15 minutes. Now let's add a speed filter to count the cars that are going more than 30 miles per hour. The top item in the graph shows about 70 to 80 unique cars that passed that intersection in the last 15 minutes. Now let's look for cars that are going about 45 miles per hour. With this search, you can see that the number of cars have reduced from the prior search. This highlights the analytic capability of this end-to-end intelligent traffic system.
The next demo shows the visualization of the entire ITS application.
The last item in our application is visualization. To visualize all the intersection, you take the camera feeds and the collected insights and map it all on easy-to-use web interface. This shows the real-time camera footage with the bounding boxes. With this interface, you can scroll the map, zoom in, zoom out, and drop into any camera feeds at any intersection. This is extremely useful for viewing anomalies and alerts. At the bottom, you can see the average speed of the vehicle in that corridor, as well as average time taken between the corridors.
The next industry that can benefit from cameras and AI is manufacturing and industrial. The type of problem that we can solve in this space are fault detection in a semiconductor inspection, faulty components on PCB, or parts inspection in a factory. A lot of these fault detection and inspection happens manually right now, which is time-consuming and error-prone. With AI and deep learning, we can automate a lot of the manual inspection. Manufacturing inspection works more so with high-resolution images than videos. The detection techniques that is very useful in industrial application is segmentation. In segmentation, you highlight the exact outline of the object, pixel to pixel, as compared to the bounding box in an object detection. The image on the left shows a tiny defect on the upper left-hand side. Defect this small is very easy to overlook if you're doing it manually. But with AI, the tiniest defect will be highlighted, as you can see on the right-hand side. This shows the segmentation overlay over the defect. With industrial inspection in mind, DeepStream 4.0 can support segmentation models, monochrome models, and hardware-accelerated JPEG decode. We have expanded the functionality of the NVINFR plugin to handle segmentation natively. To use a segmentation network, change the network type property in the NVINFR plugin. This enables segmentation in the NVINFR. For more options, please see the NVINFR chapter of the plugins manual. To visualize the segmentation results, we have introduced a new plugin called NVSeg Visual. The segmentation pipeline will look very similar to the object detection pipeline, with difference being you have to use the NVSeg Visual after your NVINFR. In the model directory of the SDK, we have included a UNet segmentation model for industrial and semantic application. Also packaged in the SDK is a reference example that runs the segmentation network. We have added a new metadata field for segmentation. This contains class number, pixel class map, width, and height. Processing and understanding high-resolution images is vital for industrial inspection. This requires a lot of computing resources if done on the CPU. In DeepStream 4.0, we're bringing the GPU-accelerated JPEG decoding capability in one of our plugins. It uses NVIDIA's NVJPEG library for decoding. It can accept JPEG or motion JPEG format and output RGBA buffers. The remaining pipeline will look very similar to the video streaming pipeline, with batching, inference, and display to follow. To show the usage of this plugin, we're shipping with a sample application that can process multiple JPEG images. This plugin can also support color and grayscale images. Another industry that we can transform with cameras and AI is warehouse logistics. We can improve and optimize the supply chain of distribution center by automating redundant manual processes, which can increase employee productivity and safety. One of the use cases in warehouse is detecting and flagging packages on a conveyor belt. For this, we partnered with Microsoft Azure and Lenovo to build a proof of concept solution where we flag packages if they are on the wrong conveyor belt. This can quickly generate an alert, and the packages can be removed before it is sent further. Our solution relied on multiple cameras over the conveyor belt connected to an edge device. The camera input goes into the DeepStream container, which will use AI to perceive pixels to insights. These insights are then sent to the Azure IoT Edge runtime. The business logic services created by Lenovo will generate notification services and communicate back to the runtime. Finally, all the telemetry data is transferred to the Azure IoT Central. Now let's see this system in action. The next demo that you're going to see was put together by Lenovo to show a proof of concept of what we are building. So let's jump into the demo. In the short clip that you saw, you can see that one package was deemed good and the other was deemed bad. The package is detected and checked if it belonged in the correct conveyor belt. If it doesn't, then the red light will flash on the conveyor belt indicating an illegal package. For packages that are good, no light appears. The way the packages are sorted and flagged in this demo is based on the QR code on the box. The application has to first detect the box in a frame and then scan the QR code. Let's see how this reference application was designed using DeepStream SDK. Here's the entire pipeline implemented in DeepStream with connection to Azure IoT Central. What's unique in this pipeline is we've implemented a custom GStreamer plugin to read the QR code of the package. DeepStream offers the capability to create custom plugins and add it in the pipeline. This provides developers the flexibility to create a custom solution that fits their need. The DeepStream Developer Guide and the Plugins Manual provide information on how to create custom plugins. After the QR code plugin is the Message Converter and the Message Broker plugin. The Message Broker plugin connects to the Azure IoT Edge runtime to communicate with the Azure IoT Cloud. Finally, the entire solution is Dockerized in a deployable container. One of the ways an IoT Edge device can connect to the Azure IoT Cloud is through the IoT Edge runtime. In DeepStream, the connection to the cloud happens via the Message Broker plugin. This plugin uses the lower-level library called libNVIDIA's Azure Edge Proto to connect to the Azure Module Client. This module client is part of the Azure IoT SDK. Azure IoT SDK is a set of libraries designed to simplify the process of sending and receiving messages from the Azure IoT Hub. Detailed instructions on how to download all the dependencies can be found in the plugins manual. The Azure module needs to be inside a Docker container. The benefit to this approach is you can connect multiple apps through container to a single IoT Edge runtime. This was showed in the warehouse logistic example where we had other containers communicating simultaneously with the Azure IoT Edge runtime. In this section, we'll go over several reference examples to get started with DeepStream. These are some of the reference applications that are packaged as a part of the SDK. If you're just getting started with DeepStream, this is your starting point. All the source code is included in the package. The first app is DeepStream Test 1. This is a basic hello world to DeepStream. This walks you through basic building block, going from a single video source from a file to decoding, batching, inference, and then outputting the results with bounding boxes on the screen. Test 2 builds on Test 1 and adds a secondary network after object detection. The secondary network is a classifier. This shows the multiple networks running in the single pipeline. Test 3 adds multiple video capability to Test 1. With Test 3, you can process multiple streams which are displayed on a screen in a 2D tile array. Test 4 adds the IoT services through the Message Broker plugin. It provides steps to connect to the Azure IoT Cloud or send messages to the server using Kafka Message Broker. In addition to this, we have several more reference applications in the sample apps directory. Once you graduate from this, please take a look at other examples. We also provide an end-to-end DeepStream app in the package. This app is slightly more complex than the 4 test apps, but offers full configurability through a config file. All the parameters are controlled from the config file. For input, you can specify any number of input sources, any type of input sources, so this could be a file, RTSP, camera, as well as the input resolution. For inference, you can control the batch sizes, the network type, the network resolution, the detection interval, GPU ID, and more. In addition, you can specify options for a secondary network and a tracker. For viewing, you can control how you want to tile your output in a 2D array. This is useful when you have multiple inputs. You can also control the color and the feature of the on-screen display, such as the bounding box and the text. And finally, for output, there are options available to view the streams on a screen with the metadata, or store it in a file, or stream it out over RTSP. This is an app to quickly prototype or demo your pipeline and see how it works in DeepStream. All the source code is available in the source directory. In DeepStream 4.0, we're bringing the ability to run YOLO models natively. We can run inference using the YOLO models from the NVINFR plugin. This plugin uses TensorRT, NVIDIA's inference accelerator. The NVINFR plugin takes the NV12 or RGBA buffer plus batch metadata as inputs. This plugin consists of preprocessing, inference, and bounding box parsing. In the preprocessing step, the image is scaled or cropped to meet the resolution of the network. Because not all layers in YOLO models are supported in TensorRT, we have to add few additional steps. First, you need to create a CUDA engine using the CUDA engine API in DeepStream. Then you create the YOLO network. Then, using the iPlugin interface in TensorRT, you create the custom implementation for the unsupported layers. And finally, the last part parses the bounding boxes for the detected objects. To work with the output layer of the YOLO model, we have provided custom bounding box parsing function. All the source code to create YOLO network and custom bounding box is provided in the source code in the source directory. We support YOLO v3, Tiny v3, YOLO v2, and Tiny YOLO v2 networks on DeepStream 4.0. In addition, we've added a tutorial on the documentation page to integrate custom YOLO model in DeepStream YOLO app. DeepStream can now be deployed in Docker containers for our data center GPUs such as T4 and V100. The containers are available on NVIDIA NGC. The NVIDIA Container Runtime enables GPU acceleration for applications running in Docker containers. In a GPU-accelerated container, CUDA driver needs to be installed on the host OS with Docker engine running on top. The CUDA Toolkit, Video Codec SDK, and TensorRT are installed inside the container. And running on top of this container is the DeepStream SDK and DeepStream application. For GPUs, we are providing a development and deployment containers. The container comes with all the lower-level dependencies to build your applications inside the container. DeepStream 4.0 brings the goodness and portability of containers on JETSON platform through the NVIDIA Container Runtime for JETSON. This adds the capability of running GPU-enabled containers on JETSON devices. Leveraging this capability, DeepStream 4.0 can run inside containers on JETSON device using the Docker images made available on NGC. The DeepStream container expects CUDA, TensorRT, and VisionWorks to be installed on the JETSON device. These libraries are mounted within the container from the host. This ensures our containers remain small and portable for edge devices. Another difference between the GPU container is the JETSON containers are for deployment only. This was done primarily to reduce the size of the containers. The deployment containers do not support DeepStream software development within the container. You will need to build the application natively on a JETSON target and create the containers by adding the binary to your Docker images. Alternatively, you can generate JETSON containers from your workstation using the instructions provided in the NVIDIA Container Runtime for JETSON documentation. Please use the NGC link to access the JETSON container. Let's walk through the metadata structure in DeepStream 4.0. The metadata structure in 4.0 is very different than the previous releases. The metadata structure starts with the batch level metadata, NVDS batch meta, marked as 1 on the slide. This metadata is generated inside the NVStream Mux plugin. This is the first level of hierarchy. Inside of batch meta is the frame meta, NVDS frame meta, shown as number 2 on the slide. The number of frame meta inside the batch meta is equal to the batch size of the stream mux. Frame meta is the second level of the hierarchy. From the frame meta, you can reference object meta and display meta, third level of hierarchy. The number of object meta is equal to the number of objects detected in a frame. This metadata is created inside the NVInfer plugin. The display meta is for displaying boxes and text on the frame. From object meta, you can further reference classifier meta. This is only created if there are multiple networks. For example, if you detect a car and next you want to detect the color of the car or the type of the car, this information will be stored in the classifier meta. This is the fourth level of metadata hierarchy. You can find more information about the metadata structure in our migration guide and the plugins manual. These are some of the resources available to get started with DeepStream. We have another webinar on DeepStream that is scheduled to go live on September 10th. It will be hosted by Jason Dickey, Senior Solutions Architect at NVIDIA. That webinar will go into greater technical details about building streaming framework. So please sign up if you want to learn about building your application using DeepStream. You can sign up using the link on this slide. We have a few technical blogs on our site and few examples on GitHub to get started. You can also pull DeepStream containers off of NGC.
Thank you everyone for attending this webinar. Hopefully now you have a basic understanding of what DeepStream is and how you can use it to build streaming pipeline. So download DeepStream, explore our Metropolis platform, and check out the support forums. Thank you. Now I'll open up for Q&A. So fire away. Thank you guys for attending the webinar. Now I'll open up for Q&A. Please use the Q&A widget to post your questions. I got a question saying, are there any tutorials on how to use and install DeepStream on Nano and to run a custom YOLO v3 model? You can install DeepStream using the instructions on the download page. All the documentation such as development guide, plugins manual are available on docs.nvidia. The best place to start would be the 4 tests that I mentioned in the webinar. All the source code is available for that app
And then you can also advance to the end-to-end app, which is slightly more advanced, but we provide the source code for that. And for YOLO, we provide support for YOLO models, and we have an example to run YOLO V3, V2, Tiny YOLO V3, and Tiny YOLO V2 models. You can take a look at the example. In addition to that, we also have a tutorial on the docs.nvidia that you can use to customize your YOLO model. Thanks. Hey, one of the questions I received was, do you have a roadmap for Docker containers in AGX Xavier? Currently, the Docker container only supports or doesn't support DLA or video input using a CSI camera. And we're actually looking at that, and we are actively pursuing that, and we're looking at our container runtime, and we will provide an update when we have that. Another question I received is, are there any plans to host DeepStream on Azure or AWS cloud? So DeepStream 4.0 supports Microsoft Azure. We have plugins to directly send your messages to the Azure IoT. For AWS, it is part of our roadmap. We are looking at integrating with AWS. If you want to run DeepStream on any of the cloud provider, you can currently run it as long as they're running NVIDIA GPUs. So if you can run it on V100 GPU or T4 GPUs on the cloud, then it does support DeepStream on cloud. Are all the NVINFERs primary and secondary running in parallel? And if yes, how is the CUDA resources allocated and scheduled? So each of the NVINFERs are a separate thread, and they are scheduled as per the priority. The CUDA also has a scheduler which allocates and manages these resources. Next question is, are there any guides to using DeepStream with Azure IoT Central? We've provided details in the documentation as well as the README file to use DeepStream and connect to the Azure IoT Hub. Is grayscale supported when using video streams or only for JPEG? Grayscale is actually supported for both video and JPEG. Will the video of this talk will be available? Yes, you can watch it on demand using the link in the answer. One of the questions was, are all the plugins open source? No. Right now, we're offering, we're opening source for a few of the plugins. So our decoder plugin, the Infer, the inference plugin, and the 2 message broker plugins. Those are the 4 plugins which are open source. All of we provide source code for it. All of our sample apps are open. You can download those. You can edit those as you wish. One of the questions I received is it free to use DeepStream in commercial product? Yes, DeepStream is freely available. You can download it from our product page, or you can pull the container from NGC and use it in your product. One of the questions is, can the smart parking application, the 360-degree application that we provided in 3.0, will that work in 4.0? Actually, at this moment, it doesn't. We're currently in process of migrating over to 4.0. There are a couple of new plugins that needs to be migrated from 3.0 to 4.0. So we're in process of migrating that. So please stay tuned. Once we have that, we will provide an update either via email or through the forums. One of the questions is migration from DeepStream 3.0 to 4.0. One comment I have on that is there's major changes from 3.0 to 4.0. 4.0, we unified the platforms for all NVIDIA platforms for JETSON as well as T4s and V100. So there are major changes in our code. So there's for that, the 3.0 code won't work directly in 4.0. So we provided a detailed migration guide, and you can download that. You can also access that from our docs.nvidia page, and you can take a look at the migration guide to see how and what you need to migrate your application. One of the question is, does DeepStream SDK include Azure IoT Edge Stack or just the Azure IoT SDK? DeepStream supports Azure IoT Edge. The Azure IoT Edge Stack is not part of the SDK, but we can connect to it, and there are instructions in our documentation as well as README file to connect to the Azure IoT. So what all the dependencies that you need to download to connect to the Azure IoT. One of the question is, does Docker support TX2? Yes, it does. So we have a separate container for all the JETSON platforms. So we have a separate container for JETSON and GPUs. So the JETSON container that we have called DeepStream L4T, that can be run on JETSON Nano all the way up to JETSON AGX Xavier. So TX1, TX2, all the JETSON, you can use that Docker container. One of the question is the DeepStream API, is it in C, C++, or is it in Python? So right now it's only in C and C++, but Python is definitely on our roadmap for DeepStream. Many of the DeepStream reference applications are configuration driven, are associated configs. So the question here is this the suggested area to begin modification for custom application? Yes, so the DeepStream app that we provide, the end-to-end app that takes in, that you can configure it for multiple video streams and multiple networks. And as well as you can output either to a screen or you can save it on a file. So that's a very good example to begin and start developing an application. So that's slightly more advanced, but if you are just starting out, then the best place for you to start is start with a test one, which is a very basic DeepStream app, which just shows you how to build a pipeline. And then slowly 2, 3, and 4 kind of builds up on that, and then DeepStream app is a full end-to-end app. So that's generally how you should approach if you're building your own applications. Right, this is a question about performance. How many camera feed is tested by NVIDIA for object tracking and detection? So we provide a performance table on our product page. In addition to that, there's a link that takes you to our documentation, our development guide, which you can use it to see how many we can configure. So for example, what we see on a Nano is we can run up to 8 cameras simultaneously doing detection. And for our T4s, we can run as many as 64 camera streams. So if you want to replicate this performance, take a look at our performance section in our dev guide. One of the questions is, can the solution be adjusted for higher resolution video feeds? Yes, we do support resolution up to 4K, and you can run multiple video feeds up to 4K. I'll answer one more question after this, and then we'll post the answers on. We'll post the answers on our DeepStream forum. Next question, is there a plugin or possibility to analyze text out of a video stream like license plates or billboards? Not right now. We cannot support OCR plugins, but we plan to have that in our future roadmap. Thank you guys for attending this webinar. I'll post the answers on our forum. And to kind of summarize the talk, so you can use DeepStream for any streaming analytic. If you want to analyze videos or images, and if you want to understanding using AI, DeepStream is a solution. And we offer connectivity with various message broker and cloud to build your application and then transfer data to the cloud. And you can also integrate our transfer learning toolkit with the DeepStream. And one final thing, we do have another DeepStream webinar that is going to be a more technical deep dive that is scheduled to go live on September 9th. So please register for that and attend that. So that will give you a more technical, more detailed technical overview of DeepStream. And thank you guys for attending.
Hey, thank you for attending our webinar. We appreciate your company here, and we hope you enjoyed it. This will be available shortly, so you can replay it and share it on our webpage. And we hope to hear and be here for you soon. Thank you.